shear stress is the third stress we are going to study in our structures, because we studied the axial stress in the first place, the very simple one, just forces acting perpendicular to our cross sections and then distributed uniformly. So very simple to calculate. So you have a force divided by an area, and that's it. We saw this in part the last lesson in combined stress, because in combined stress we have a combination between this axial stress, very simple, plus the bending stress, which is a little bit more complex because the moments that the bending produce, there is a distribution, a linear distribution of the stresses from a maximum in compression to a minimum zero at the level of the neutral axis, and after an increment linear increment until you reach the maximum in tension, for example. But there is more stresses. For example, there are these shear stresses produced by the shear forces we calculated before. If you remember, in simple support beams and in cantilever beams, we had been describing the distribution of these internal shear forces through the shear force diagram. So this shear force diagram these shear forces will produce shear stresses on every cross section that will be different in value depending on the value of the shear force, of course. So as you see in the screen, there is a very simple way of describing the shear force, which is called an average shear force. But this shear force is not accurate because this shear force is basically have the same value as an axial force. So we are saying here that if we have, for example, a shear force internally in a beam, doesn't matter if it's simply supported or cantilever, and the value of this shear force is V, if we divide this V by the area of the cross section, we're going to have a value in units of stresses, but this is the same as we did for axial stresses. So we are going to have a uniform distribution of the shear stresses. Yes, I can change that for you to see more clearly. So basically, you will have that the shear stress has the value of an axial stress. But this is not the proper way of describing the distribution of the shear stresses, because if you try to be more accurate, you will realize, for reasons I will explain after, that the actual distribution of the shear stresses is not uniform, but is parabolic. So we have three types of distributions already. We have uniform distribution for the axial stresses, we have linear distribution for the bending stresses, and we have parabolic distribution for the shear stresses. In here, for example, you have the distribution of the shear stresses for a rectangular cross section, which is parabolic. So this means that we start at the extreme on top of the beam, for example, in here where we know that the bending stresses are maximum, we have a zero shear stress that will increase with this parabolic function until reach the maximum in the middle, exactly at the position of the neutral axis, where the bending stresses is equal to 0, remember? So we start discussing about the relationship between these stresses, because these stresses act on the cross section altogether, remember that. So basically this is the shape we know a priori, so we know the shape independently of the actual values, but we know a priori that the maximum will be in the middle in the position of the neutral axis for this rectangular cross section, and actually for every cross section. So the neutral axis will be our reference to define the maximum shear stress we are going to have in a cross section. So this is the proper way to describe the shear stress. But if you are on the field and you want to have a very roughly, calculation, what you can do is you can run this calculation, because it's very simple to do by hand. And if you study in the notes this derivation in here in the second page of your notes, you will realize that there is this relationship Let me just find where is the relationship in here. There is a relationship between the average shear stress and the actual shear stress in the position of the axial of the neutral axis. So basically, after a derivation, you find that the maximum shear stress at the neutral axis is equal to 1.5 multiplied by the average. So this allowed you to run a very quickly calculation when you are, for example, if you are in a hurry and you want to have an idea of these maximum shear stresses for some reason, you can just apply the maximum shear stress, the actual maximum shear stress is equal to 50% more than the average shear stress, which is basically the shear force divided by the area of the cross section. The derivation is not necessary for you to know because this is not going to be part of the exam, but if you are interested in derivations, mathematical derivation of this kind of relationship, it's good for you to take a look. And if you have any question, as usual, just let me know. But the formula that we are going to use in our practice, resolving these exercises of shear stresses, is this formula you have in here. Remember, we have a formula for the bending stress that give us our linear distribution of bending stresses. We have a similar formula for the shear stress as well. And these are the elements you need to define, or the elements you need for feeding your formula. So the shear stress at any point of the cross section is going to be equal to the shear force in the first place. The shear force, remember, is a force that is in the same direction as the cross section. You are going to define an area, a particular area we're going to discuss in more details after. And you're going to have a distance from this area we're going to define from the center of this area we're going to define to the neutral axis, this y in here. You will have the moment of inertia corresponding to the cross section in the horizontal direction in this case, and multiply by a distance v. We are going to see in more details in the exercise what is exactly this, but this basically is the width of the cross section at the position where we are calculating the shear force. So we are going to we will need to calculate this value for every point we are going to study in the cross section. So if we have a parabolic distribution, you will need a minimum of 3 values to have a proper shape of the curve, because with 3 values is enough to to have the shape. But if you want to calculate at more points, you can do it. Actually, you can calculate at infinite number of points, because it's going to work for every single point with the reference, using as a reference the neutral axis. We will see in more detail right now. So what are all these elements we need to define then? I will maybe just let me copy this formula in here to see the meaning. So as I said, we'll increase the size. This is the formula we are going to use. And for example, let's say we want to calculate the shear force at this position in particular. So this red value in here will give us the value of the shear force at this particular point. So if we want to do that, we are going to have to introduce in this formula the shear force. The shear force will be constant in this cross section, because this shear force is the shear force for the shear force diagram. So at a particular cross section, this shear force will be constant for every single value we calculate in here, because it's always the same value. The area we are talking about in here is a particular area. So if we are going to analyze the shear force at this red line in here, this value in here, we need to define the area on top of this line. So what we do is we define this rectangle in here, which is B, is the width, and the height is whatever it is, because depending on the size of this cross section, this value will be one or another. And the area is just the area of this rectangle. So very simple. This area A prime is going to be B times the height in here. The distance we are going to introduce in the formula will be the distance from the center of this area we define it on top of the fiber where we are calculating the shear stress till the neutral axis. The neutral axis is always the reference. And we are going to divide all these three values by the moment of inertia regarding the axis XX. This is the axis XX. And we are going to multiply by B. And B is the width of this rectangular cross-section. And B will be constant for rectangular cross-section because B is constant for rectangular cross-section. So this is clearly seen here in the skin of the cross-section. And that's it basically. So if we want to calculate, for example, the maximum moment of inertia in here, the area defined will be the whole half of this cross-section, as we are going to see in the examples. So it's a little bit more complicated than the formula for the bending stresses, but still a very simple formula to fit and to evaluate the shear stresses at every point. Good. What else? Let me just check. Okay. If you ask yourself why the distribution of these shear stresses are parabolics and are not linear, or why we cannot use this rectangular distribution in here, this uniform distribution in here, is because if you remember from previous lessons, and if not, you can check again, the way that the shear forces works are very particular. So the shear forces appear in a cross section, not only in the cross section itself, but in other sections that are perpendicular to the cross section you are analyzing. For example, let's say this is a beam in 3D, and this is the cross section in here, the cross section where we are going to establish the distribution of the shear stresses, and this is the top surface of the beam. You know, because the top surface of the beam is not suffering any sort of a stress, that, and because it's free, that there is no any shear force in here, because the shear stresses, sorry, there is no any shear stresses in here, because in order to have a shear stress, you need to have another element producing some sort of friction in here. And because this top surface is absolutely free, because this is just, let's say, a beam subjected to the self-weight, for example, it's impossible for you to have any sort of a stress, because you don't have any other structural element producing any sort of shear stress. So at this fiber on top, you have to have this value. If you analyze the first value immediately in contact with the first fiber on top of the beam, equal to 0, because these two has to be equal. There is an equation that is called Cauchy equation that says that the shear stresses has to converge to an edge like this, and the values need to be the same. This is a mathematical equation that has to be fulfilled in order to keep the equilibrium, because if not, if this doesn't happen, you will have a rotation of this element or a cross section, and this is something that doesn't happen in reality. So in order for this set of forces that define the shear stress of states in these elements, you need to have the same values in all of them in order to keep the equilibrium. This is a demonstration of why we start with 0, and what will happen in the middle, where we have the maximum, is that the maximum shear stress will be in the direction of the cross section, but will be as well in another plane, which is in correspondence with the neutral plane. So in the neutral plane, we are going to have the maximum shear stresses, not only on the cross section, but in any section that's defined or are defined in the horizontal direction as well. There is a video you will see after in the second part of the lessons where you are going to see these effects explained in a better way, and with a graph and with a movie, where you probably will understand better what I'm trying to say here. So the important thing to do the calculation properly is to know that the distribution is parabolic. Once we know the distribution is parabolic and we know that the maximum is in correspondence with the neutral axis, the only thing you have to do, you have to fit this formula in here. So it's not going to be that difficult. I will delete this one from my notes. Okay. And I will save it. Okay, let's focus the attention now in this exercise, the first one. And remember, please, because, for example, in this exercise, they say a rectangular section 30 millimeters times 40 millimeters, as you can see in the figure, supports a vertical shear force of 72 kilonewtons. And after that, the problem asks you to determine the average vertical shear stress, the maximum vertical shear stress, and the vertical shear stress at intervals of 5 millimeters from the neutral axis, and hence plot the shear stress distribution. So basically, you need to do all the calculations with the formula we have studied before. But remember that this force, this data in here, this 72 kilonewtons, is the shear force you have in a beam, for example. This could be part of the simple supportive beam, or this could be part of the cantilever beam, or this could be part of a column, for example, and you have the information about the shear force directly. But it's important for you to know that this is part of another problem, and this section probably will be subjected to bending stresses as well, and axial stresses, why not, and maybe torsion. So this is a partial analysis of the stresses, focusing the attention only on the shear stresses. But this cross section eventually will be part of another structure subjected to more stresses. Okay, after saying that, we can focus the attention on the calculations in here. So very, very simple. The three things we need to calculate are the average vertical stress, which is absolutely simple because it's 72 divided by the area. The maximum will be to work with our formula we started before, and after we have the distribution to get the parabolic diagrams next to the cross section. So if we study in here the formulas, it's very simple. As I said, what the notes are saying are doing in here is just transforming this V in kilonewtons to newtons, multiplying by 1,000 basically, and dividing by the cross section area in millimeters. So this is the reason why the result is in Newton per square millimeters. Very, very simple. Because we know the results of the derivation I explained before, and we know that the maximum shear stress in the middle will be 1.5 multiplied by the average, we can do this directly, or we can use the other formula. So if we multiply 1.5 times 60, we have 90, which is the maximum in the middle, as we know. The next calculation in the notes are the moment of inertia regarding the axis X, which is the moment of inertia of this rectangle. So it's 30, which is the width, times 40 cubed divided by 12. Very simple. The value, the result is 160,000 millimeters to the fourth. And after we do what the third point is asking, because this is point A, this is point B, and the next point, the point C in the questions for this example are to divide the cross section from the neutral axis. So we have half of the cross section only here. Because the cross section is in total 40 millimeters, half will be 20, and this 20 will be divided in 4 different intervals. From the neutral axis to 5, from the neutral axis to 10, from the neutral axis to 15, and from the neutral axis to the extreme, which is 20 millimeters. And we can call, for example, these points with letters. This will be A, B, C, D, and E. Just for reference, at the point A, then the distance Y is from the neutral axis to A, 20 millimeters. The area is equal to 0 millimeters square, because from this point of reference and on top, there is not any more cross section. So the area is equal to 0. The width is 30 for all the cases, because this is a rectangular cross section. So if we try to fit the formula with the values, V is 72 kilonewtons. You can transform to newtons if you want. The area is equal to 0, so automatically everything is equal to 0. But if you want to replace this, well, this will be equal to y in this case because there is no any area. But doesn't matter what you apply, what are the values you feed this formula because this a prime is equal to 0 already. So we have demonstrated one more time that the shear stress in a rectangular cross section in the fiber on top is equal to 0, and the same thing will happen with the fiber at the bottom. The next point to consider is the point B. The point B is at a distance of 15 millimeters from the neutral axis, and because it's clear in here is 5 plus 5 is 15. The area will be the area that is in shadow in here. So it's 30 millimeters, which is constant for the whole cross section, multiplied by 5 millimeters. This is the area of this rectangle. We define it in here on top of the fiber we are analyzing. We are analyzing the fiber B, remember? So this distance is not the same as this one, because this distance is from the very center of the rectangle we have defined before to the neutral axis. So it's from this very center in here to the very center, which is in correspondence with the neutral axis. And this is the reason why it's 17.5. So it's 15 plus half 5. And B is always 30, as I said, because this is a rectangular cross section. So you can resolve, for example, the multiplication between the area and the distance to the centroid. And this is the value. This is called a moment of area. So if you want to add to your notes, because it's not there, this is what we call a moment of area. This is not a second moment of area, and this is the reason why the result is millimeters cubed. So it's just an area multiplied by a distance. So this moment of area can be introduced in here, because in here we have the moment of area, A prime times Y. And this is the value of the shear force. This is the value of the moment of inertia, and this is the value of the B, which is constant in this particular exercise because the cross section is a rectangle. And this is the value of the shear stress at the fiber B. Okay. If you go to the next one, if we go to the fiber C, so we are here now. Our rectangle is a little bit bigger. It's actually the double than before. So the area is going to be the double as well. It's 30 times 10 because it's all this shadow section in here. The distance from the centroid to this rectangle to the neutral axis is 15 millimeters in this case. B is constant, equal to 30 millimeters. The moment of area is a little bit bigger because we have a bigger surface. And if we replace all these values in the formula, we have the same shear force as usual because it's the same cross section. The moment of area is a little bit bigger because the area is bigger. The moment of inertia is the same, and B is the same. And this is a bigger shear stress at the position C. So as you see, we started with 0 at A. This is for B, 39.4, and at C we have 67.5. The next point to be analyzed is the point D. Now we are in here, so our area will be on top of this fiber. We define it in here. So now the area will be 30 times 15, so a little bit bigger again. The distance from the centroid to the neutral axis will be 12.5 because it's 5 plus 5 plus 5 divided by 2. B is 30, it's a constant. The moment of area is the area of the new rectangle multiplied by the distance to the very center, from the very center to the very center. A little bit bigger because the area is bigger. And we feed our formula, so 72,000 is the same as usual. The moment of area is this value we calculated before. The moment of inertia is the same, and B is always constant because this is a rectangular cross section. Again, a bigger shear force because we are reaching the maximum, which is at the level of the neutral axis. Finally, if you want to check the calculation you did before with the simplified formula of 1.5 multiplied by the average of the shear stresses, you just do the same thing we did before. So we are at the fiber E now. So we are going to define as a area of reference the whole half of the cross section. which is 30 times 20, is 600 millimeters to a square. The area from barycenter to barycenter is 10 in this case, as is clear in the scheme. B is constant. The moment of area is 6,000 millimeters cubed. We replace all these values in our formula one more time, and we get exactly the same value as we did before. This is a practical demonstration that the formula we derive at the beginning of the explanation that give you the relationship between the average shear stress and the maximum shear stress at the level of the neutral axis is right, because the values are exactly the same. In the calculation in here, we did the calculation and we got 90 Newton per square millimeters. And when we use the proper formula, the formula that give you the shear stresses at every point, you got exactly the same value. In order to complete this exercise, and this is important for your exam because you need to be very clear in your exam to demonstrate your knowledge, because remember that your exam will be an open book exam. So it's very, very important for you to be very clear in the way you communicate what you know, because if not, you will lose some marks just because you are not communicating properly. And a way to communicate properly your knowledge and the result of your exercises is to show diagrams, because engineers, we understand a common language in the whole world, which is through the diagrams. So the bending moment diagram, the shear force diagram, the axial force diagrams, and the diagrams for stresses are extremely important. So in this figure in here, it's very clear that we did a series of calculations, and actually you can improve this one, including in here the distances of 5 millimeters to be 100% sure that where is the levels of these different values of stresses in here. So it's very clear that the maximum is 90. It's very clear that the units are Newton per square millimeters. It's very clear that this is the neutral axis. It's very clear that this is the cross section. Just because this is in a scale, it's clear that these other values are at 5, 5, 5, and 5. But if you add 5 in here, it's not. It is going to be even better, because you don't need even to measure with a ruler the position to guess exactly where the calculations were made. So this is a very, very good diagram to show that these are the values of the shear force, the shear stresses at this cross section at the different levels. And we know as well that this is symmetric. So if you add a symbol of symmetry in here, will be even better, because we know that the same values we are going to have at the other side of the neutral axis, because this diagram is symmetric. We know that this is symmetric because this is an information that we have a priori in terms of shear stresses for a rectangular cross section. So this is the way to present, and this is very, very important because in exams usually, because you are in a rush, you tend to produce diagrams that are not very clear. So my advice is try to do this diagram very, very clear for me to see that you know what you are doing and you know the relationship between the diagrams and the cross section, for example, and the relationship between the shear forces and the shear stresses, etc., and etc. Use units every time. I know it's painful because you have to write one and another time the same units, but it's important for me to see the units and to see that you understand what you are doing, because this is exercise not about replacing numbers only, it's knowing exactly what we are doing, why we are doing, and the use of units is mandatory, because a number without units have no meaning, because I don't know what are the units you are using. Okay, good. We have 15 more minutes. We have time to cover this, the next exercise. And it's interesting because this cross section is different to the previous one. So in this case, the example is the distribution of shear stress in an I section. So we have an I section with the dimensions you can see in the screen. So it's double symmetric. So we expect to have a diagram which will be double symmetric, will be symmetric as well regarding the neutral axis because the symmetry. So we know that the shear force is 500 kilonewtons in this case. So we have much more shear force than in the previous exercise, because in the previous one we had 72 only. So we need to determine the vertical shear stress at A, B, C, and D. So now we don't have a uniform distribution of this line for doing the analysis, but we have defined 4 different points. We have A, we have B, we have C, which is this corner here, and we have D, which is in correspondence with the neutral axis. As you see in the first place, you need to take in consideration that the value of B, the width of the cross section, will depend on the position of the fiber you are analyzing. For example, for A, B will be 100. For B, B will be 100 again. For C, which is considered a point X immediately after the corner, will be only 6 millimeters, and for D will be 6 millimeters as well. So this is the key for this exercise, because the B will change. And the area, of course, will change as well, and distances and everything. So we are going to see case by case. So all the dimensions are in millimeters. By inspection, the center is at the center of the section. This is because this section is double symmetric. We know that the center is in the middle directly, so half of 100 and half of this 320. So very simple to locate. It's not a big problem. The moment of inertia for this case is a little bit more complicated than before. In this case, in the exercise, you have one way of doing it, but you know that you can do it in different ways, the calculation of the moment of inertia. I'm not going to review the moment of inertia again because you know how to do it already. But you have a way of doing it here, so you can study in details the way that the moment of inertia was calculated. So let's focus the attention in the fiber A. So it's the first fiber we have on top of the double symmetric I section. And as it happened in the rectangular cross section, the area on top of the fiber will be equal to 0, and this will produce a 0 shear force in your formula. So there is not much analysis to do in this case, because the area on top of the fiber A is equal to 0. What happened at the point B? So now we are at the fiber B, so we are immediately at the end of this rectangle in here in the screen. So the area defined to do the analysis will be on top, which is the whole rectangle you can see in the screen. So very simple, the area will be 100 times 10, which is 1000 millimeters square. The distance from the barycenter of this rectangle to the neutral axis will be 150 plus 5, which is equal to 155 millimeters. B, the width of the cross section defined to do the analysis is 100, because it's from here to here. Then the moment of area will be 1000 times this distance. It's this value here, 155,000 millimeters to the cube. And if we feed the formula, we know we have 500,000, which is 500 kilonewton multiplied by 1000 to express this value in newtons, multiplied by this value of the moment of area we calculated before, divided the moment of inertia, and this is B, which is 100 in this case. And this is the value for the shear stress at this particular point B we have analyzed it right now. The point C is immediately after this final fiber of this rectangle, this winding here. So automatically we have to notice that B will change suddenly from 100 to 6 millimeters. And this is the key for the next result. This is why it's in red in here. So the area is exactly the same because C and B are practically at the same position, but C is a little bit under, but the area is not going to change because this C is very, very close to B. So the area is exactly the same. The distance from barycenters to barycenter is exactly the same. What changed is the value of B from 100 to 6 millimeters suddenly. The moment of area will be exactly the same because we didn't change the area. We didn't change the distance from barycenter to barycenter. And if we fit this formula, the only significant change we're going to have, or actually the only change we're going to have is B, because all the other values are exactly the same as the previous formula, as you can see. The only change is 100 to 6. But because the change is sudden and is considerably, the value of the shear force, the shear stress, sorry, changed a lot. So from 12.6, we go to 210 Newton per square millimeters. So you see that the influence or the effect of this change in B is considerably in our distribution of shear stresses. There is a note in here because this is the key. So at C, there is a sudden change of the value of V from 100 to 6 millimeters. This produces a sudden change in the value of the shear stress as it's shown in the diagram. So we continue our calculation. We're going to see the diagram at the end. So we are at the point D now. So we are at the position of the maximum shear stress. So B is equal to 6 millimeters again. Now, the thing is that the area that we have to define on top of the line where we're doing the analysis are two rectangles, these two rectangles, this rectangle in here and this rectangle in here. And you have two distances from centroid to the neutral axis and to the centroid, from the centroid to the neutral axis. And these distances are 155 and 75 in this case, for obvious reasons in the geometrical analysis of this cross section. So the moment of area will be, we have two parts, the moment of area of this rectangle and the moment of area of this rectangle on the web. So you have the numbers in there. I don't want to go number by number, but this is the value for the moment of area of this T on top of the neutral axis. So feeding the formula to evaluate the shear stress, we replace the values. B is going to be 6 again because we are in the middle of the web. And this is the final value and the maximum value for the shear stresses. In this case, because this is a nice section, we cannot use the simplified version of the shear stresses multiplying 1.5 multiplied by the average, because this is a nice section. This simplification works only for rectangular cross section. So don't use the simplified formula because you are going to get the wrong result. You have to apply the general formula for this case, in this case, because this is a nice section, so you cannot use the simplified version. But this is what is different, and this is what is interesting in this exercise in particular. In here, in this diagram again, it's very clear what's happened. You start with 0. You have a first value at the end of this wind equal to 12.6. And after, because the sudden change in the V from 100 to 6, you have a jump in here in the value of the shear stresses, and you go from 12.6 to 210. And after that, you have a parabolic distribution in here until you reach the maximum value of the shear stresses, which is equal to 301 Newton per square millimeters. All this distribution in here from 0 to 12.6 is parabolics, and from 200 and 301 is parabolics as well, because we still have the distribution, this parabolic distribution of the shear stresses, but because the shape of the section, we have this particular shape, which is still parabolic, but with these sudden changes in the shear stresses. So the first example you have is a nice section. It's exactly the same exercise as we covered before, so I'm not going to go on the details of this exercise because just the numbers are different, but the procedure and the formulas and the way of doing the calculation is exactly the same. So let's see what's happened when you have a C section. So in terms of the calculations regarding the shear stresses, when you have a C section or a channel, they call it a channel section as well, the calculations are exactly the same as the I section, because the only moment of inertia you need to evaluate in here is the moment of inertia regarding the axis XX, which are the axis of corresponding to the neutral axis, because we are thinking that these cross section are part of a beam. So they are subjected to bending stresses and shear stresses at the same time. And this is the reason why the C section or the channel section for in terms of shear stresses will be exactly the same as the T section. In here, for example, you see that you don't need even to locate exactly the position of the centroid for this exercise, because the only thing you need to know is the centroid is on the neutral axis, that is this axis XX basically, which is in the middle of the height of this C-section. In terms of the shape of the distribution of the shear stresses for the C-section is exactly the same as the I-section, because you have the sudden change in the width from 60 to 10 in this case, for example, and you will get a kind of shape like this one for the I-section as well for the C-section. So there is no much changes, so I don't need to go for details. What I'm going to do is I'm going to go for the details for the T-section, because this is certainly a little bit different to the I-section and to the C-section and to the rectangular section, which was the first one. And this exercise is a little bit more open, let's say, because basically what the exercise said, that you have a single symmetric T-section in this case, single symmetric because the symmetry is only regarding the vertical axis. So the section is subjected to a vertical shear force of 100 kilonewtons or 100,000 newtons. So the question is asking you to sketch the vertical shear stress distribution through the section depth, indicating the salient values. So the salient values is referred to the values at this particular point we choose to do the calculation. For example, this will be A, B, C, and D in correspondence with the centroid of this T section. Evidently, because this is a T section, we know that the centroid will be on this vertical axis that pass through the middle of this T, but we need to locate first the position of the centroid to know exactly where is the neutral axis and the centroid, because at this level you will have the maximum shear stresses for this cross section. So there is a previous calculation of the location of the centroid in order to be able to know where we are going to have the maximum. So here is the calculation of the centroid. We did all this calculation before, so I'm not going to explain again. It's just anyway summation of moments of this rectangle and this rectangle, and comparing with the moment of the total area of this T multiplied by this distance from this reference at the bottom regarding the position of the centroid, and doing this moment, as you know, you will get the position of the centroid. So this is simple. This is not the topic today. So there is another thing you have to calculate, that is not a topic from today. Just is once you know the position of the centroid, you will be able to calculate the moment of inertia regarding the barycentric axis X that pass through G. So in here you have the calculation. So you have to calculate the moment of inertia of every rectangle and multiply and plus the area of this rectangle on top, for example, multiplied by the distance from the centroid of this rectangle to the centroid of the whole T, and plus the moment of inertia of this rectangle, which is the web of the T, plus the area of the web multiplied by the distance from this centroid in here, the centroid of the web, to the centroid of the whole T, and you get the moment of inertia in regarding the axis X. So once you have this calculated, what you do is you do exactly as we did before in terms of calculation of the, I will put in this size, as we did before with the I section. So you go point by point. So you will define a series of points. You will define the point E in this corner, the point B in the next corner, the point C in this corner in between the web and the top of the T. And the point D will be the intersection of the neutral axis and the web in here in this point. So once you define this point, you start doing the calculation as usual. The first point you have, which is the point A, is at this level. So on top of this fiber in here, on top of the T, you won't have any area. You won't have any area to run calculation. So the area will be equal to 0, as you see in this example. and in this part of the calculation, B will be 200, the distance Y will be from the centroid to the top of the T equal to 80 millimeters. But because this area is equal to 0, the whole calculation here will be equal to 0. So the first stress, the first shear stress you have at the fiber A is equal to 0. For the second point, which is the point B, the distance will be, I don't know. Okay, the distance Y is 60 millimeters, is from D to B. Is simply to show the position of this axis, this neutral axis. But the area will be the same area. No, the area will be the area of this rectangle in here, which is in shadow. So the area will be 200 multiplied by 20 is 4,000 millimeters square. For some reason, the units are not here, but they should be there. So if you can add to your notes, the unit will be a good idea. This distance Y is the distance from the center of the rectangle to the center of the whole T, which is the location of the neutral axis. So it's 70 millimeters. B is 200 millimeters because we're analyzing this fiber in here. And the moment of area will be the area of the rectangle multiplied by the distance from centroid to centroid, which is 280,000 millimeter cubes, because it's a surface multiplied by a distance. After that, we have all the elements to replace in our formula, and we find that, well, this is converted to newtons. This is the moment of area. This is the moment of inertia, and this is B, 200 millimeters. And we find that at B, the shear stress is 1.92 Newton per square millimeters. The next point to analyze is the point C, and at the point C, what's changed, the only thing that changed actually is the value of B, because B is only 8 millimeters at that point in particular, because it's just the section which is exactly after the fiber B. And the area is the same, the distance is the same, so everything is the same with the exception of the value of B. So if we replace this value in the formula for evaluating the shear stress at the point C, we have the same V, the same shear force, the same moment of area, the same moment of inertia, and the only change is we change this, instead of 200, we have only 8. So because the change will be considerably, you have 200 in here, and we are going to use 8 in here, of course, the value for the shear stress will increase considerably. So we increase the value from 192 to 48.1 Newton per square millimeters. Finally, the final calculation we are going to do is the calculation at the point D, where we expect to have the maximum shear stress. And Y is equal to 0 in there, just to show the location. B will be 8 because we are at this fiber. And now we are going to have, as an area on top of the fiber, we are analyzing the area of the rectangle on top and the area of this portion of the web of this T section. So the moment of area will be then the area of this rectangle multiplied by the distance from the centroid to the center of the whole T, which is 70, as you see here. And the other area here will be 8, the width of this web, multiplied by 60, so the area of this rectangle, multiplied by the distance from this centroid to the center of the whole T, which is 30 millimeters. Replacing values, this is 294,400 millimeter cubes. We replace all these values in the formula to evaluate the shear stress. And we have the same V, the same the moment of area we calculated before, the moment of inertia, which is constant for the whole T, and the value of 8, which is the width at the web. And the value of the shear stress will be 50.6 Newton per millimeter square, which is greater than the previous one, because at the level of the neutral axis, we have the maximum value. In here, there is another calculation. There is another calculation that is made at minus 270 from the neutral axis. So the calculation is at the point E, basically. And when we do the calculation under the neutral axis, what we consider as an area is the area from the neutral axis and at the bottom. And this is the reason why they say that at this level E, if you consider at the bottom what area you have, the area is equal to 0. So you do the opposite as you do on top of the neutral axis when you are working at the bottom of the neutral axis. So in this case, the area is 0, and this is the reason why they finalize calculating that the shear stress at the level E is equal to 0. You can consider the area on top anyway, and you will find that the result is 0 anyway, but you can do this by yourself if you want to consider at this point all this area. Check if calculating with the formula you have the same results. So what else? Okay, this is the most important thing about this this exercise, because this is the shape of the distribution for the shear stresses on the T section is a little bit different to the previous ones. So, for example, these are the resumed results in this diagram. So you have 192 for the point B. We calculated 0 for A, 48.1 for the point B, and 50.6 for the point D. And this is the maximum one because this is in correspondence with the neutral axis. So you see that the distribution is still parabolic. So from 0 to 192, this is a parabolic distribution. You have the jump in here because the sudden change from 200 to 8 millimeters for the fiber B and C. You have the maximum in here, but the distribution from 48.1 to 50.6 and to 0 again is still parabolic. So the distribution is always parabolic. The only thing is, depending on the changes of the width of the cross section, you will have these sudden changes in the values of the shear stresses. So as we see, let's say, a resume of all these calculations, I will show here. I did a kind of resuming here for you to see the differences. And this is a good exercise to be sure that we are communicating the results properly. So when you have a rectangular cross section like this, remember that the value of our exercise in particular was 72,000 newtons. We have this distribution, this parabolic distribution of the shear stresses, and it's continuous just because the B, the width of the cross section, is constant along the whole height of the cross section. This is the reason why this is so nice and this shape is uniform and continuous, because there is no any change more than the distances and the areas you consider for the different points to evaluate the shear stresses. The units are always in Newton per square millimeter. This is the position of the neutral axis. The dimensions are expressed in millimeters, and all here is clear. You can add, if you want, maybe the distances between these different lines to be more precise, but the idea is to provide a kind of diagram like this. When you have an I section or you have a channel or a C section, as you saw in the, you can do for the C section the same calculation and get the diagram, and you will see that the diagram will be the same shape. You will have this parabolic distribution in every and will be symmetric because the cross section is symmetric. It's double symmetric, actually. It's symmetric regarding the vertical axis and symmetric regarding the horizontal axis, which is the neutral axis. And the only difference you see with respect with the T section is that half of the section from the neutral axis on top, the distribution is exactly the same as an I section, but from the neutral axis and to the bottom of the section, of course, the distribution is continuous because there is no any sudden change again in the width of the cross section. So it's very important to know what is the shape we're going to expect in terms of the distribution of shear stresses in order to to have a simple calculation of the values and just connect the values with the appropriate curve, which is a parabolic function in this case. Okay. So as you see, the exercises are very repetitive. So the calculations are exactly the same all the time. You just need to be very confident in the calculation of moment of inertia and the location of the centroid. So this is the reason why we have studied moment of inertia and the location of the centroid for different sections in the first semester, because these calculations are useful for you to evaluate the bending stresses and the shear stresses. For the axial stresses, these calculations are not necessary because for axial stresses, you only use the area, you don't use the moment of inertia. But for bending stresses and for shear stresses, you use the moment of inertia, then you need to know the location of the centroid. You will see in the in future sessions that there is another shear stress that is produced by another type of force that are called torsion. The torsion is something that we are going to study after, so I'm not going to give you any details, but torsions produce a shear stress as well that can be acting on top of the shear stress produced by bending forces that act on beams, simple supported beam or cantilever beams.